We're going to continue with some lectures about pattern-forming systems, in particular looking at spatial temporal systems, which under perturbation or under parametric changes change their behaviors. And what we'd like to do is use all of the perturbation theory we've been using thus far to try to understand the kind of patterns that arise in many spatial temporal systems. What are the analytic techniques we can get to approximate the kind of behaviors we see in practice? This is an important field because you see pattern formation throughout physics and engineering and biology. A lot of systems that exhibit spatial temporal low dimensional type structures, and part of the reason what we'd like to understand is just how do those occur, when do they go unstable, what kind of patterns would form under instability, and so we want to bring in an analytic framework to evaluate this. So we're going to start off with the very generic spatial temporal system. Here it is. And you can think of this U as actually a vector of first order equations. So it doesn't have to just be a scalar. But the idea is that you have some nonlinear evolution equation here. This is some nonlinear PDE. So U of t is equal to n. N prescribes the PDE. It's dependent upon U, Ux, spatial variables, and importantly on some parameter mu. So the parameter mu is going to act like our bifurcation parameter. And we've already started studying bifurcation theory. So what we're going to know is that as I change this mu, the fundamental behavior of this system can change or bifurcate to some new solutions. And then the question is, what are the characteristics of those new solutions? So this is what we want to look at. And what we're really considering here then is going to be expanding about some kind of given solution. So for instance, normally what we do in perturbation theory is do some kind of formal regular expansion. We're going to do something like that here. We're going to say I have some solution U naught, and I'm going to look plus epsilon U tilde. And the epsilon is small, so this U tilde is correction to U naught. And the really big question to ask is what happens to U tilde around some bifurcation? If U tilde grows, it means this U naught solution is unstable. If U tilde goes to 0 or stays bounded, then U naught is considered to be stable. So these are the kind of things that we want to do here to try to understand the resulting dynamics of this system. So when we do this formal perturbation expansion, I'm only going to keep up to order epsilon. You can go to higher order if you'd like. We've already been doing that in our perturbation expansions previously. But you just collect, and now what you're doing is you're collecting orders of PDEs. So at first order, you get the leading order equation, U naught t and an n of U naught, so presumably you have a solution to this. And oftentimes the solution to this is just the trivial solution. U naught is 0. Oftentimes many solutions have a trivial solution, and you want to understand when does the trivial solution go unstable, and when it goes unstable, what happens to the system. At next order, you get the evolution equation for U tilde. And notice that because this is a perturbation expansion, the evolution dynamics is linear. So the L operator, so we've been talking a lot about these differential operators. I now have one here, L. Okay? And so the characteristics of that linear operator are going to determine quite a bit of the dynamics that I would expect to see in this spatial temporal system. So that's what we're doing here. We're doing this perturbation expansion, plug in this solution with a small perturbation, do your perturbation expansion, and then start to understand what is the dynamics of U tilde. If U tilde is growing, it means that this U naught solution is unstable because this will start to get big. And then you can't use this expansion anymore because you have this big contribution from U tilde. If U tilde stays small or goes to 0, then U naught is actually a stable solution. So here's how we're going to understand the stability. What we're going to do is a separation of variables. We're going to say that this U tilde is going to separate space and time. So some v of x times e to the lambda t. Now by putting this in, notice what we are actually saying specifically about the lambda t. So if the real part of lambda, if it's positive, then this thing here will lead to exponential growth. If the real part is negative, then it'll be exponentially decaying. And if I have imaginary components, there's going to be oscillations in the system. So there's a nice interpretation to what those eigenvalues lambda are going to be, because in fact this is going to be an eigenvalue, because when you put this in to this equation here. Here's your linearized equation. You put in that solution form. T only shows up right here. So then this is going to lead to, when you plug that in, the following eigenvalue problem. LV equals lambda V. And this is something we've been studying throughout the course, the beginning of the course when we were talking about eigenfunction decompositions. And now here's a perfect opportunity to do an eigenfunction decomposition. And what I'm really interested in is, what are the eigenvalues lambda? Do they have a positive real part? Do they have real parts that are negative? Do they have complex eigenvalues? All of this matters quite a bit because it really determines the nature of the solution that I'm going to get out of this. So that's what we're going to go after. And the other thing I want to point out is that the eigenvalues themselves depend upon the parameter mu. So this is going to be very important for us in considering pattern-forming systems. Because what we're going to do now is combine sort of these eigenfunction expansion ideas with bifurcation theory. In other words, as we have the solution, it's going to be a function of mu, and the mu will often change the location of the eigenvalues. And what you care about with this parameter mu are there eigenvalues that cross from being the imaginary axis, so the real part is negative, to the real part being positive. At that point, you're going to experience an instability because the real part is now positive and the solution, this perturbation solution, is going to grow. Okay? So that's going to be one of our major tasks, to start to understand when I cross those eigenvalues, any single eigenvalue crosses from a real part being negative to a real part being positive, I'm going to have an instability, and it's going to lead to a bifurcation. And that's what we want to quantify. So just keep that in mind. This is really important in what we're doing here. So let me give you some examples. So I thought this would be good just to illustrate it with some specific examples. I'm going to start off here with a nonlinear PD, what's called the Fisher-Kolmogorov equation. So you have ut minus uxx. This is something like the heat equation. But now I have a u cubed, and then I have some kind of linear growth term. So I have diffusion, I have nonlinear damping, linear growth. And the question is, what kind of resulting dynamics do I get out of this system? Okay, it's a simple model in many ways, but it shows a lot of rich behaviors. So what you can do is first look at the equilibrium solutions, and that means set ut equals to 0. And when you do that, you get here, in fact, I'm also going to look at spatially homogeneous solutions, in other words, that are independent of x. So then that's going to drop out the ut and uxx. I'm just going to get u cubed minus mu u is equal to 0. And then there are three solution branches. There's the trivial solution, u equals 0. And then there's the solution branch, u naught equals plus or minus square mu. Okay? So those are the solution branches. And notice it looks a lot like a pitchfork at this point, right? So once I drop these terms out, or even if I drop the uxx, the normal form is the pitchfork bifurcation. I go from from one solution to three solutions when mu goes from positive to negative. So I can linearize about these solutions, but now when I linearize about these solutions, I do have the uxx term here, I have the ut. So here's what I get. The linearized solution is given, evolution is given by here. So I have the linear operator, it's given right by here. And that linear operator contains the u tilde xx. And so what I want to understand is, what are the dynamics of this linearized PDE? So one way to deal with this PDE is just to Fourier transform it in space. And what I'm thinking about here is this thing lives on an infinite domain. X goes from negative infinity to infinity, and t starts at time 0 to some large time. And so I'm just going to Fourier transform this, and it's going to turn it into a very simple first order ODE. Here it is. So k is the wave number of the Fourier transform. And so I have this term here times u hat, and u hat is the Fourier transform of u tilde. And that's easy to solve exactly, and here it is. This is the solution to this. It's a first order ODE with constant coefficients. You just try an exponential solution and you have it. You're done. And so your solution is given by here. U naught hat is equal to e to the minus omega t. Okay, and what I call that omega is this term here, k squared plus 3 u naught squared minus mu. And what I really care about is, when is that omega positive, when is it negative? And it depends on what the wave number is. Notice here, if k squared is big enough, then this whole thing here will be, in fact, positive. So that means it will be damped. But there are some low frequencies which can have this be negative. In other words, if mu is big enough, you could imagine this thing here being negative. And in fact, then it would lead to growth for certain bands of frequencies, spatial frequencies k. In fact, that's exactly what happens. We can look at this and say, hey, look, all I want to know is when is this quantity positive or negative? All the k values for which this is positive means that, or this thing means it's stable. So if k squared is big enough, it's going to be positive. However, whenever this is negative, the k values that are such that make this negative are going to lead to growing solutions. So a band of unstable frequencies. And in fact, that's exactly what you find in this Fisher-Kolmogorov equation. You can actually do a simulation of this. And what I've done here is I've actually just looked at the stability of the zero solution. And here's the zero solution. I added some noise to it to perturb it. And this is its evolution in time. And notice what happens. What happens is this zero solution is unstable. There's a band of frequencies that go unstable, and it jumps to a different type of solution. In fact, the solutions it jumps to are those constant solutions with their square root u or square root minus u down here. And so so there's these constant solutions that it jumps to when it goes unstable from the zero solution. Much like the pitchfork, when you go across the bifurcation, you jump up to either the top branch or the bottom branch. This is exactly what it does here spatially. And in fact, if you look at this thing in the frequency domain, this is exactly what it looks like. So what you see here are those wave numbers for which the real part of the exponential is positive, or means you're going to get exponential growth. And so this exponential growth is right here. And in fact, those frequencies are represented here. Those are the frequencies that grow initially, and then you get this resulting pattern. So you bifurcate from the zero solution, and you jump to another branch of solutions, which are the square root mu and minus mu. So this is this one example where we can work everything out pretty nicely analytically. And you can start to understand the nature of the pattern that's formed by just simply doing this calculation of linearization and trying a solution of the form e to the lambda t plus omega x, or plus kx. Let's do this with another problem. This is going to be the Kuramoto-Sivashinsky equation. Here it is. It's got a fourth order diffusion, second order diffusion, which is backward. So this here will create backward diffusion, which is regularized by a fourth order diffusion. And then you have this nonlinear advection term UUX. Okay, so this is a very interesting equation that leads to lots and rich dynamics, and quite a bit of studies have done on the Kuramoto-Sivashinsky equation. What we want to understand is just some of the basic structures that we might see in practice, sort of in some sense your first superficial look at the patterns that are formed in Kuramoto-Sivashinsky. So the first thing we're going to do is we're going to take the zero solution and we're going to linearize about it. So let's just say if I have a base solution which is 0, which in fact is satisfied, u equals 0 is the solution to this, and I ask the question, is that zero solution stable or unstable? So I perturb around it, and here is my linearized evolution. There it is. It's a fourth order diffusion equation. I can put in a Fourier transform this, and here's what you get. So first of all, you Fourier transform this. Here's what you get. The fourth derivative gives you a k fourth, second derivative k squared, and then you can write down your solution, and here it is. And in this solution here, notice the exponent has a k squared minus mu k to the fourth. So for k very large, this k to the fourth will dominate eventually, and the large wave numbers will be stable. But for the low wave numbers, for instance, k is small, this k squared will dominate, and in fact, so you're going to have a band of unstable frequencies. At k equals 0 itself, this thing is just e to the 0t. So you can't, it's sort of neutrally stable. So what we're expecting to see in this is a band of unstable frequencies, which the size of the band of that frequency depends largely on the parameter mu. Okay? So What does this look like in practice? Well, here's some simulations of the Kuramoto-Sivashinsky equation. We can run this. This is for mu being 0.005 and 0.4. For 0.005, the band of unstable frequencies is much bigger. In fact, what I'm showing you here, here's the evolution. This is a topographical look at the evolution equation. Look at these very interesting patterns that form in the system. These sort of roll patterns, but it's chaotic. And this is well known in this system, and at least for this parameter regime. And so you can see this very interesting pattern, but there's a dominant frequencies that appear in the dynamics, right? There's some kind of periodic type structure in there. And if you look at the unstable modes, this is the evolution of Fourier domain, then you can see the rise of these unstable bands of frequencies, which are exactly, here is in fact your prediction analytically. You get this double bump solution where you have these bands of unstable frequencies. So in fact, that's exactly what happens. These bands of unstable frequencies start generating growth at specific frequencies. In fact, the dotted lines here that you see, those are the dominant, most rapidly growing frequencies, which correspond to the frequency basically that you're seeing here. That's the dominant structure in this evolution, is those frequencies. As mu gets bigger, you collapse that window of unstable modes, and here you go. This is what you see here, and in fact, here's the evolution. It's basically just essentially one sinusoidal function that's sitting in there. So just this very simple-minded linear stability analysis and looking at the real and imaginary parts of the exponential behavior tells us a great deal about some of the patterns we actually see in practice in this system. So do another example and then talk about more general theory. So this is the nonlinear Schrödinger equation. Here, it's got an I in front of it, so this is the complex function I, square root negative 1. And so this is going to be some complex evolution. And so when you actually look at this, you start to say, do I have solutions? There is the zero solution, but I'm actually going to look at this solution right here. This is a plane wave solution. In other words, the plane wave solution, where this comes from is optics, is a constant amplitude solution. And there it is. The constant amplitude is A, and it's got this nonlinear phase evolution, e to the I mod A squared t. So if you look at just the absolute value of this thing, it looks like a constant amplitude solution, but the phase itself is winding up in a nonlinear way depending upon what the amplitude A is of this solution. So the question is, what's the stability of this plane wave? So same thing as before, we can perturb around the plane wave. And the way I'm going to do it here is I'm going to factor out a common phase. So u of xt is equal to the amplitude plus perturbations to the amplitude, all multiplied by e to the I mod A squared t. This just makes it simpler to work with, simpler to do the algebra, is to remove a common factor of this nonlinear phase. And when you do this, what you find for the linearized evolution is this governing equation here, which what you see is it's a first order ODE, it's first order in time here. It's got uxx, and you get coupling because of the nonlinear Schrödinger couples you to the complex conjugate. Okay, so this is going to be an important thing. So the field itself is complex. So you have a real imaginary part, and now u is not just coupled to itself, but to its complex conjugate, which is where I is minus I. You can break this up into the real imaginary parts, and we'll do so in a minute, but first I'm going to just Fourier transform it, just like I've been doing with all the others. Here's the Fourier transform of this. Now I have everything in terms of u hat. I still have to take care of that real and imaginary part. So I can always write this, break u hat up into a real part and an imaginary part. If I plug that back in, what I end up with is the following first order ODE, which for the real and imaginary part of the evolution. Here it is. And in fact, what I can find for the stability is I can look at the eigenvalues of this, which is easy to do. I find this here as those omega squared, which is telling me something about the exponent itself. And I'm very interested in this curve here. This is where, in fact, I have neutral growth. So k, if I change the k around, I can go from positive to negative and make this unstable or stable. In fact, what I'm finding here is if I find my band of unstable frequencies, here they are. So here's the K. This is this line back here. This is omega squared equals minus k squared plus 4. So notice it's positive in some bands, and then it's negative in the rest of the bands. So what I've got here is a plot of what's going on with my e to the omega t. So all I care about is if that real part's positive, I'm going to grow, and if it's negative, I'm going to decay. And notice that depending upon the frequency, it's either growing or decaying. So I have these bands that are unstable. And remember, the solution is the constant solution. And the constant solution itself has a Fourier signature, which is the zero frequency, or that's the DC offset. So that's what you see here in the Fourier domain, is this DC offset. And then you see here the growth of these two side bands, and this is what happens in the simulation itself. This thing is modulationally unstable. You start with this plane wave, and it starts to develop these instabilities, which is, if you look at it from a pattern-forming system, notice what happens. You see the growth of a periodic pattern. And that periodic pattern is determined by these unstable frequencies. You can actually explicitly compute the period of the frequencies that are actually the dominant growth modes. So this is a well-known phenomenon in optical sciences and in fiber optics, this modulational instability. You put in a plane wave solution, and it starts to, in fact, go unstable, but in a very specific way. It generates oscillations with prescribed frequencies, which is your modulational instability frequencies. So let's step back, and I've given you 3 examples, but now what I want to talk about is, like, can we start looking at this in a more general, abstract way? So let's do that. So I'm going to start off here with some pattern-forming system, some PDE. Depends upon some parameter mu. That's going to be a bifurcation parameter. The pattern here has been exactly what we've been doing in a lot of the perturbation theory, which is, suppose I have a solution, let's call it U naught, and suppose I'm perturbing around that solution. So I'm going to look at this U tilde. And what I want to understand is what happens to U tilde. What happens to U tilde, if it gets big or small, determines the stability of this U naught solution. So I plug this into the governing equations. I collect orders. So at order 1, I have some nonlinear evolution equation. So in other words, this is the leading order solution. But now, at next order, I get an evolution equation for U tilde. In other words, I'm getting a linear evolution for what's going on with the perturbation of this solution. And now what we're going to do, once we have that linearized equation, the goal is to plug in this equation here. And I've rewritten it slightly because I want interpretability. What I mean by that is the following. I'm going to put in solutions of the form that are like this. E to the lambda t plus ikx. Now the reason I've done this specific form is because the lambda here, so the way this is going to be decomposed is I care about this lambda. Is the lambda, the real part, positive or the real part negative? That's going to determine if it's growing or decaying. And by the way, if there's an imaginary component to lambda, when it's growing, it's going to grow with oscillations. And it's going to decay with oscillations. So in time, the lambda is going to tell me if I'm growing or decaying with or without oscillations in time. Now, at the bifurcation point, I also care about k. If k is, in particular, what is k? If k is 0, then this is e to the 0x. That means there is no spatial pattern. In other words, e to the I0x is just a constant. So there's something across the entire domain, the solution is constant. So it's like a plane wave. However, if k is non-zero, in other words, there's going to be this dispersion relationship, is what it's called, which relates lambda and k. If k is non-zero, then it's e to the I kx, which is some kind of oscillatory pattern. In fact, I just showed you that in the case of the nonlinear Schrödinger, where there was a modulational instability. So when this thing went unstable, if k is non-zero, you're going to see a spatial pattern develop. So there's this really interesting interplay between lambda and k when instability happens. And there's some prototype instabilities that you're going to be able to observe depending upon what those two values are. And so that's what we're really after. So in fact, Let's assume I have some bifurcation at some value of mu equals mu of c. Okay? So at that point, the solution goes unstable. I linearize about that solution. I plug in this type of solution here from the linearized evolution, and I ask the question, what's going on with lambda and k? And it's going to tell me a great deal about the evolution dynamics itself. So first, let's talk about lambda. There's kind of two cases for lambda. One of them is that the eigenvalues look something like this. Lambda, as I go from mu less than mu of c to mu greater than mu of c, in other words, as I walk through the bifurcation, two eigenvalues go from their real part being negative to the real part being positive, but with non-zero imaginary components. So when that happens, this solution, which was stable, will go unstable because now the real part's positive, and it'll do so in such a way where the lambda values, the imaginary parts, are non-zero, which means you're going to see oscillations at characteristic frequencies at where they cross this imaginary axis. Okay? When we talked about Hopf bifurcations in bifurcation theory, when it went unstable, you saw oscillatory temporal dynamics. That's exactly what this is looking like in this context. When these two eigenvalues cross the right half plane at non-zero imaginary components of the lambda t that you have there, then you're going to get oscillations. You also have the other possibility where you go through the bifurcation, you go from negative real part being negative to positive, but there is no imaginary component, in which case you're just going to get exponential growth. Okay? Now what about the k values? There's a couple things that could happen in the k case. You could have a scenario like this. When it goes unstable, you could have a structure where your k is, how k looks as a function of the instability, it could look like this. In fact, I showed you these band of unstable modes, and you could have, they're centered around non-zero values of k, let's say minus k naught or k naught. And so when you go unstable, what I'm showing you here is as I move through this, this is mu less than the bifurcation, mu at the bifurcation, mu just after the bifurcation. So in other words, right after the bifurcation, I have a non-trivial k, which is the largest growth mode. If that's the case, when it goes unstable, you're going to see a spatial pattern centered at this with this kind of frequency content. You could also have it go unstable like this, which is here is below the bifurcation, at the bifurcation, past the bifurcation, and the most unstable mode is centered around k equals 0. In other words, you're just going to get an entire pattern to grow, but there's no modulation on that structure. So these are the canonical cases that can happen in this kind of scenario here. And so what you want to look at is when I do my linear stability, I really need to know the relationships between lambda and k. And that's called the dispersion relationship. And here are the pictures. These are the canonical things that can happen in pattern formation. So what I'm showing you here for each of these are three-dimensional pictures. And one can think about it as this direction here, space, time is this direction, and then this is the amplitude. So what I'm going to show you is these four possible cases. The first type of bifurcation that can happen is this one here. I go from one solution, and as I walk past the bifurcation, it goes unstable with k naught and omega naught being 0. What does this mean? Well, if I come back to here, it means that when I walk across here, I'm in this scenario here, I walked across, and when I walked across here, the omega naught is where I hit this. It's 0. Versus here, this is non-zero. So I walk across it here, and with this kind of going across the boundary there. So in other words, with k equals 0. And in that case, I get a kind of a very simple dynamics. This thing goes unstable. There's some growth mode, but no oscillations in time, no oscillations in space. I just go to some new solution, let's say. Okay? So that's what you would get, sort of in some sense, the most boring case. Here, this is more like the Hopf bifurcation. What you're seeing here is when I go unstable. So in other words, over here, I'm left of the bifurcation. Over here, I'm to the right of the bifurcation. Right here is the bifurcation. At that point, when I go across, if the wave number, k naught, is 0, but when I walk across, I walk across with omega naught not being 0. In other words, when I cross the axis, I look like this. There's some omega naughts that are non-zero. The real imaginary parts, when I walk across, are non-zero at some omega naught. That means I'm going to have temporal oscillations. And that's exactly what you see here. You go unstable, and it starts to oscillate in time. So you have this growth and oscillation at a specific frequency, which is the frequency when your eigenvalues cross from the negative, from being in the real half part being negative to the real being positive. Okay? So it's a second type of instability. So you get this instability, and what I'm showing you down here is two more, where now, suppose I cross the axis where the k naught is non-zero. Both these up here, k naught is 0, and now I'm going to come to this case here, when your unstable bands of frequencies are not centered at 0. Okay, I've already shown you this for the Kuramoto-Sivashinsky. I already showed you this for the Nonlinear Schrödinger and its modulational instability. So we've already seen examples that when things go unstable, I get a modulation. And that means that I have bands of frequencies that are dominating the instability. And so here, you can go unstable in the following way. Here again, you start off stable, and as you hit the bifurcation, at this bifurcation, we're going to be in a scenario where the k naught is non-zero, so I have some non-trivial spatial pattern forming, and here I'm also assuming that omega naught is 0. So in other words, the combination here is an eigenvalue that crosses the plane like this, so with a 0, its frequency is 0, but its unstable bands are non-zero. So what you're going to get is this pattern right here as you walk over. And then the final case is when you walk over, you have a non-trivial spatial pattern, and there's a temporal pattern because the two eigenvalues cross with non-zero frequencies, and that's here, right there. So it's this Egg-Cartan pattern. So you get spatial and temporal oscillations in this case. And what you're looking at in that case is that you have this combination of this here, two eigenvalues, crossing with non-trivial frequencies and crossing with non-trivial unstable bands. So you get some dominant growth mode k naughts and some dominant frequencies omega naught, and that's exactly what drives this pattern right here. So these are just the canonical forms. What's important about these pictures is you should meditate upon them. Make sure you understand them, because these, much like normal forms, these are so your canonical forms that can happen, right? When you go unstable, you either have you're either going to go unstable and you have exponentially growing solutions in time, with or without frequency oscillations. And when it goes unstable, your spatial structure will either be centered around a band of frequency, spatial frequency 0, or some non-trivial band of frequency not 0. And so these are the four cases that you would have to consider driving instability of patterns and the possible patterns that can potentially arise. Everything's determined by the eigenvalues of the linearized operator. And so you have to understand this dispersion relationship to completely understand the pattern forming instability. We're going to build on this, but this is really the underlying mechanisms of all spatial temporal systems. And you can look at so many spatial temporal systems, whether you look at the sky and cloud formation, or patterns in water, or patterns in biology. These mechanisms are sort of these very generic structures that you see everywhere in nature, and is driven by some very simple mathematical ideas, right? These are canonical abstractions that, just like the normal forms, are sort of, in some sense, the prototype instabilities that are going to occur in all systems that you might consider in practice. So I want to finish there, and we'll continue building on this very, I think, very interesting field of pattern formation by considering more how we can use some of our mathematical techniques in perturbation theory to go beyond what we just talked about here.